morning, and good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Gorewski, and I will be your host for today. This is a really, really busy week at Exploring by the Seat of Your Pants. We have lots of events happening, some days 3 or 4 or more live events. It's World Rhino Day tomorrow on Friday, so we have a whole series of events. And then it's also Climate Week in New York City. So we've teamed up with the Explorers Club to host a series of events with scientists and researchers, filmmakers and explorers to really bring us into the world of climate change. So these are people who are exploring and researching what's happening. They're documenting those changes so that we can see them back home. And then, of course, many of them are looking for solutions to the climate crisis that we are facing right now. So if you visit exploringbytheseat.com and then under the events tab, you will find Climate Week NYC, and you can still find some events that we have coming up. We have been exploring all kinds of things, from Paul Salopek and his Out of Eden walk, where he's basically walking from Africa through Asia, North America, and then down through South America, following the journey of our ancestors and telling the stories of people ranging from technology to climate change to mass migration. We have polar bear experts. We have people studying sea ice and everything in between. Citizen science. It is a jam-packed week. So we hope to see you joining us in other events or catching some of the recordings. Now, our event today, we have the incredible Melinda Webster joining us. Melinda is a polar scientist at the University of Washington's Applied Physics Laboratory, so their Polar Science Center. And her work is using satellites and airborne technology and modeling to study frozen oceans in both the Arctic and the Antarctic environments. So she's been on a lot of different polar expeditions by aircraft, by ship, by snowmobile, so that she can collect measurements about sea ice and understand more about how it applies to our Earth systems. So I'm going to bring Melinda in live with us right now. Hey, Melinda, how are you?
Hey, good to see you. Thanks for having me.
Oh, Melinda, we're really excited to have you. We have a great group of classrooms backstage. We're going to get to see into their classrooms in a little bit. We have lots more tuning in on YouTube, and we're excited to learn a little bit more about the sea ice research you're doing.
Oh, awesome. I wouldn't pass an opportunity to talk with you about sea ice. It's my favorite topic.
Excellent. Well, I am going to let you take over the screen for a little bit, and yeah, let's get into it.
Okay, can you see my screen?
We've got it.
Okay, awesome. Thanks again for letting me join you guys. This is really great. I love sharing some of the science that my colleagues and I are doing in both the Arctic and the Antarctic. So I want to give you the takeaway message now that sea ice is super awesome and it is very, very important for regulating our climate. So let's go into what sea ice is, and especially let's start out where it is. So sea ice, it's the frozen part of the ocean. And if you were to guess, where is the ocean actually frozen? You might say it's at the poles, right? The North Pole and the South Pole, and you'd be 50% right. This is where Arctic sea ice is. So you'll notice on the left, this is a bird's eye view of the Arctic. The sea ice cover there is basically the frozen ocean surrounded by land. Meanwhile, in the Antarctic, it's this mass or this big block of land surrounded by sea ice. So it's kind of like the flip-flop between the two. So even though they're very different sea ice environments, they are incredibly important to our climate system and to the functioning of Earth's climate. So to explain why they're important, I'll go through some of the key highlights of why sea ice is awesome. Of course, its superpower is its high albedo. Maybe you guys have heard of albedo. What it means is the reflectivity of the surface. So to give you an idea of why sea ice is so powerful, is it's reflecting about 80% of the sunlight back into space, especially if it has snow on its surface. And to compare that to the ocean, if it were just completely melted ice and it was an open ocean, we'd only be seeing about 7% of that sunlight reflected back into space. And that's a huge difference. Now, it's not just about sunlight being reflected that's important about sea ice or why it's important. It's also important from an oceanography perspective or the perspective of ocean circulation. When ice forms. So these little crystals of ice begin to freeze at the very top of the ocean surface. A lot of that salt in the seawater is left behind. So you can probably see these tendrils on the right-hand image. That's actually salt that's sinking through the ice, or I mean, sinking through the water. Salt is heavy, it's making that water heavy, so it just sinks down, and that helps drive deep water ocean currents and ocean circulation. So it's really important in the context of how does heat and ocean circulation move around our planet. Now, sea ice is also a blanket. So if you think about the autumn, winter, and spring seasons, this is kind of when it's dark and cold, right? But sea ice is trapping all of this heat in the ocean and preventing that heat from reaching the atmosphere. So it's insulating our atmosphere. But sea ice is a very dynamic thing. It moves with the ocean currents, it moves with the winds. And so it breaks apart and it forms all these cracks and leads, and leads are just bigger cracks. And you can see here this plume of what looks like smoke. That's actually heat and water vapor that's being emitted into the atmosphere. So this helps warm the atmosphere. So you can think of all of these factors. They're kind of interconnected, and they're really important for the interactions between the atmosphere and the ocean, and as a whole for our climate. Now, another way to look at all these different processes is I just highlighted the three big ones, but there's a lot more going on with sea ice. And I like this cartoon because it captures a lot of the important processes that kind of get more into the details. It gets more into the weeds. So how the ice is moving, how it interacts with the atmosphere, especially clouds and precipitation, or even what's going on with the ecosystem. So if you look at this bottom panel, you might see some green blobs within this ice surface. So there is stuff that actually lives in the ice. And the reason this is really cool, well, there's many reasons this is really cool, is it's a fundamental part of the marine food web in the polar oceans, these little algae that live in these little channels of brine. So ice is not just, sea ice is not just pure ice. It has these little pockets of really salty water, and these creatures live in that water. But they form the base of the food web for the Arctic and Antarctic marine environments. They're also a really hot topic for thinking about where life on other planets may live. So if other planets have something like sea ice and these pockets of salty water, that would be a place where organisms could survive. So it's kind of cool from a not just an Earth perspective, but a planetary perspective. Okay, so that was a long list, or a long laundry list of why sea ice is awesome, but I wanted to now go into some of the ways we study the ice, whether that's on foot, by plane, satellite, or with models. I think now in particular is a really exciting time to be a sea ice scientist in particular, because we have more data and more measurements than ever before because of all of these advances in technology. So depending on what the problem is, and what I mean by that is, what's the scale of the problem? Is this something that's like very, very small, like the microstructure of sea ice? Then that's better suited for going out and taking field measurements. Or is this monitoring long-term changes like Arctic sea ice loss with climate change? That's something that we rely on satellite measurements for. But this boundary between going into the field in situ and remote sensing, that's becoming increasingly blurred with all the technological advances that we have. So I'm going to show some examples of how we're bringing in situ, remote sensing, and modeling all into the same problem to tackle some of these issues and these unknown things about sea ice and its role in our climate system. Now, the example I want to give here is a really cool expedition that I was lucky to be involved in called the Mosaic Expedition. And what it was is we took this ship and we deliberately froze it into the middle of the Arctic Ocean and let it drift for an entire year. So I mentioned that the ice moves with the wind and ocean currents. That's what happened. So we froze it in October pretty far north, and it drifted across the Arctic out through this area called Fram Strait near Greenland. And we did a lot of really cool science. There were more than 300 people, 300 scientists involved. It was a phenomenal experience. And what we wanted to do was to revisit this cartoon of how the sea ice interacts with the atmosphere, the ocean, and the ecosystem. And because we were there for an entire year, we could take really detailed measurements and also take coordinated measurements. So I could work with an oceanographer and a meteorologist and a biologist and share all of our results to improve our understanding. So this is a nice cartoon. I mean, it seems kind of messy, but it's actually quite clean and simplified. But this isn't how science actually looks. This is what science looks like. And this is a bird's eye view of the ice floe that we set the camp on. So you can see down here in the lower right, this little piece here, that's a ship that we stayed on. But you can see there's a lot of colors going on. These are different sites taking different measurements. So we had some areas doing drone measurements, we had oceanographic measurements, meteorological measurements, and so on. And this couldn't have been possible with a lot of coordination and teamwork. So again, this is such a cool opportunity, but I also feel really, really lucky and grateful to have had the opportunity to work with such an awesome team. So what was my piece in this with all this really cool science going on? You know, you can't do it all. You have to pick and choose which problems or which topics you're going to focus on. So what was mine? I was really excited about puddles. And another way of describing these are melt ponds. They're essentially puddles of meltwater that form on the Arctic sea ice surface. And they're really important. They are much darker than bare sea ice. So I mentioned albedo before. And I'd like to give you some context of how reflective bare sea ice is. It reflects about 70% of sunlight without snow on it. But a melt pond only reflects about 12% of sunlight. So there's a huge difference with how much sunlight is reflected and how much is absorbed, which helps warm the ice and melt it faster. Another way to think about melt ponds is that they're essentially the skylights of the Arctic sea ice cover. And that's what this figure at the top is showing you. This is an under ice view looking up towards the ice. And these bright areas are the melt ponds of the Arctic sea ice cover. So they let a lot of light through the ice into the ocean. So these are really important, but it's really hard to take good measurements of melt ponds because they are pretty complex. They change spatially and temporally quite a lot. It's hard to know where a melt pond will form and why. And it's also hard to capture what a melt pond is doing because they change so rapidly sometimes. This is an example of a rapid change in a melt pond. So this is from the North Pole Environmental Observatory from 2013. On July 27th, we had this gigantic melt pond, and then the next day it drained. So depending on when somebody takes a measurement, you won't know where the melt ponds are exactly. Now, the reason this melt pond drained is because sea ice, as it warms up, its microstructure changes. So I had mentioned these brine channels, or these pockets of liquid salty water. When they warm, they expand and they continue expanding and they become interconnected to the point that any meltwater on top can actually drain through. So it's really hard to know what melt ponds are going to do and when and where. But with Mosaic, we could take a lot of measurements with pretty high frequency. And that's what I did. Working with a really nice group of people, we did these routine surveys, which another word for taking a daily walk and dragging some instruments along. We measured the ice thickness and the snow depth. And here are some of my favorite instruments. So on the upper right, you see this little sled. It's holding an electromagnetic induction device, which sounds super fancy, but a way to think of it is this thing is creating an electromagnetic field, which is shown on the bottom right. But because the seawater is so much saltier than the ice itself, it disrupts that electromagnetic field, and we can measure that difference and estimate an ice thickness from it, which is really cool. And then on the left is a picture of me. You can see I'm super happy because I'm holding my favorite instrument. I'm using my favorite instrument. It's called a magnet probe. It's an automated snow depth probe. And what's cool about it is you see this little red basket. It can move up and down. It will sit on top of the snow or on top of the melt pond surface. but it measures the distance between that red little disc and the tip of the probe. So we can get a snow depth or a melt pond depth that way. So combining these instruments and these measurements can tell us how the snow, the melt ponds, and the ice thickness change over time, especially throughout the melt season. And this is what we're finding out. You know, this is pretty new results. It's really fun to be digging into the data. Now on the left, this light blue color, that's the daily walk that we did. It's about 2 miles long. It's really fun. And on the right is a little snippet of this walk. So I'm highlighting this little red area. And what you're seeing is kind of like a cross-section view of the ice and the snow cover. The 0 represents sea level. So just like ice cubes in your water glass, most of it sits below sea level, right? The ice itself, a little bit sits above sea level. That's what you're seeing here. So the ice thickness is quite variable along this little survey. Also, the snow depth is variable on top. Now, this is a pre-melt season snapshot. This is from early May. Melt hadn't kicked in yet. That's what the ice looked like. And a lot of questions that my colleagues and I have is, well, what does it look like after melt has really kicked in? Like, what would it look like in late July after, you know, the surface is melting, the bottom is melting, the sides are melting? What will that shape look like? And fortunately, we're able to look at the data and find out, but it's quite different. It's hard to predict what the ice is going to do. And it's all about how much sunlight is getting absorbed and melting the surface, and how much the ocean is warming and melting the ice from below, and also how the ocean is melting the sides of the ice. So we didn't expect it, for example, the ice to melt a lot more on the right side than the left. And so these are some of the physical processes that we're trying to find out. Now, the importance or the reason we need to understand the physics or why the ice behaves the way it does is we want to improve physics in climate models. Climate models are an amazing tool. They are a really cool way to understand how things change and how things respond. So for example, you can flatten Antarctica and see what the effect will be on ocean circulation. You can raise carbon dioxide and see how much sea ice loss there will be. So it's a really nice way to test hypotheses and see what the hypothetical response would be of a given thing. And we can test these models and compare them with the observations that we collect. So that's what we did in this Mosaic expedition, is we collected a lot of data, and now we're using that data to improve the climate models. So one of our first tests was to see how well does the climate model represent the albedo, the surface reflectivity, and how well does it represent melt ponds? Now, we are really excited by this result. What you're seeing is the albedo. So to give you an idea, 0 means it's totally dark, it's absorbing everything, and 1 means it's reflecting 100% of the sunlight. Now, early in the melt season, when we have snow on top of the ice, it's reflecting about 85% of the sunlight. So this light blue color, this is the model result. The dark blue color are our measurements, and you can see they overlap pretty well. I mean, it may not look like it to you, but to us, we're like, wow, this is an awesome agreement. We thought our job was done. The model is perfect. Yay. But then we started looking at the melt pond coverage. So how much of the area of the ice is covered by melt ponds? And we got a different story. So on the left, this is the ponded ice fraction. Another way to think of it is 10% of the ice area, or 20 or 30 or 40, so on, is covered by these puddles of meltwater. Now looking at the model, this light blue color, it has a lot more melt ponds than what we measured in the dark blue. It has double the amount of melt ponds. So what this shows us is the model's getting the right answer for the wrong reasons, which might seem discouraging, but actually was really exciting because it helps inform me what I need to go measure when I go out into the field next time. So next time I'm going to take a lot more melt pond albedo measurements. I'm going to measure a lot more melt ponds coverage and depth and so on to try to improve the physics of the climate models. Now, I think I'm still good on time. I have a few more slides left. I kind of want to switch gears here and talk about the sampling, how we do temporal sampling, or when we sample and the frequency of those samples. And an example of this in the background is I'm showing you 4 sets of photographs. This is 2 icebreakers, 2 ships from the Mosaic expedition, and they're rotating scientists and crew, and we're getting fresh vegetables and fruit. We're really happy. But what's cool about this is the ships are staying in place. They're not drifting at all. And the difference in the ice in the background is solely due to the ice motion. So ships are static, the ice is not. And I can't help but wonder what this means depending on when a satellite passes over and takes a measurement. So thinking about when something is measured or how frequently is really important. An example I want to give here is using a coastal radar. So you may have had some familiarity or know of ships that use radars. This is the same type of radar, except we've attached it to the bank building in Utqiagvik, Alaska. This is the northernmost point of Alaska. And this has been attached to monitor what the sea ice conditions are doing. There are many reasons that people want to know what the ice conditions are like, and I'll give some of those next. But first, I want to show you a video. Before I show you the video, I want to explain that the things that light up in red mean that the ice is moving. So again, to orient you, this is Utqiagvik, and looking out, you're looking over the sea ice in the upper left. And if things are red, that means the ice is in motion. So we're using this to see when the ice is having a breakout event, just like what you saw here. The ice kind of lit up all of a sudden and is drifting away. So this has a lot of important things going on, and there's many people interested in knowing what the ice is doing. For me, I want to know if my instrument on the ice that broke off is totally gone. Instruments are really expensive, and if you lose one like this, it can be kind of a bummer from a scientist's perspective. But for the locals there, especially those who are reliant on whaling, subsistence hunting of whales, they want to know when the ice is going to break off and open up the water, because that's where the whales come through, and then they can do their spring whaling, which is so important for the communities in coastal Alaska. This is also really important from a search and rescue perspective. If there are people out on the ice hunting and the ice breaks off, this is a way to monitor where those flows are going, so a helicopter can be sent out to rescue them. So there's a lot of common interest in knowing what the ice is doing, and it's really cool to think about sampling something like this in such a high frequency, combined with the multi-generational knowledge of people who live in Utqiagvik to understand what's going on with the sea ice. Okay, I think this is close to my last slide. This is my conclusion. There's a lot of really interesting ways to study sea ice, but I think some of the best ways is when we combine efforts and recognize what some common interests are and different tools that we can use to tackle some of these similar problems or similar questions that people have. So whether that's using remote sensing with modeling or field observations with indigenous knowledge, this can all come together to really advance what we know about sea ice, why it's important, and how it's going to change with climate change. So with that, I think I'll stop, and I'm happy to take any questions if we have time.
All right. We absolutely do have time, Melinda. Thank you for that great presentation about sea ice and its importance. And then, of course, taking us into the world where you get to get out on it and explore and see how it's changing. So really cool. That Mosaic expedition sounds like it would have been quite an exciting undertaking.
Yeah, it was incredible. Yeah, I can't speak enough about it. I only spent 5 months, not the full 12 months, but that was still a special experience.
Yeah, of course. Okay, well, before we get into Q&A, we're going to play a little Kahoot. So while you were presenting, I put a little quiz together for our classroom. So I'm going to share my screen. It's just going to take a moment here. There we go. If you want to play along today, it's kahoot.it, and then it's going to ask you for a PIN number. And there it is, right front and center for you, 730-2602. Now, if you have one-to-one technology, maybe you have tablets or Chromebooks you can use, you can play right at your seat. But if not, no big deal. Your teacher could put it up at the front of the room, and you could shout out your answers to him or her. And then if you don't have technology, well, that's okay. You can just answer the question yourself and see how you do at the end. If you're at home maybe or virtual and you have your phone or your tablet, scan that little QR code and it'll bring you right into the Kahoot. While classes and students are loading in, we've got, let's see, the smooth goat, the Arctic gnu. So that's a very good one for today. The amazing wildcat, the green sloth. Very cool. There will be 4 questions. Some are multiple choice, some are true and false. You have 20 seconds for each question. If you get the answer right, there's some points. If you get it right, but you do it really quick, you get even more. If it's wrong, it doesn't matter how fast you put in that wrong answer. There will be no points for you on that question. So let's give it maybe another 20 seconds or so. And then we will get started. If you're tuning in via YouTube, you can start putting some questions in the chat. And then after the Kahoot, we'll start bringing in some of our camera classrooms to see what kind of questions they might have. I see students with their technology there. I'm looking backstage. So they're getting ready for the Kahoot. We're going to start it really soon, though. I can see things are slowing down a little bit. So, Melinda, do you know, while we're waiting for a few more students to join, do you know when your next expedition will be?
Oh, yeah. I think I'll be going out on the ice in March to deploy some buoys, and this will be at an ice camp north of Alaska, drifting from the Beaufort Sea into the Chukchi Sea, hopefully.
Wow, very cool. Hopefully that ship will have some internet connectivity because it'll be a lot of fun to connect with you while you're in the field.
Totally.
Okay, well, I think we should get the Kahoot started because we don't want to wait too long before we get into our Q&A action. So here we go. You've got a couple seconds to prepare yourself before the first question comes at you, and then you got to be fast. You only have 20 seconds to get your answer in. So our first question, about how much sunlight does sea ice reflect back? Is it 15%, 45%, 60%, or around 80%? So 15, 45%, 60%, or around 80%. We have lots of answers in already. There's 5 seconds left to get your answer in. All right. Good job, crew. 80% is the correct answer. So it does reflect a lot of sunlight back out of the atmosphere. So the fast elk was fast indeed. They are in that first spot. But right behind them, the expert sea lion. Let's see what happens here. So our next question is a little true and false. Sea ice can trap heat in the ocean. Is that true? Or is that false? Sea ice can trap heat in the ocean. True or false? All right, you've got a few more seconds to decide. True or false? Sea ice can trap heat in the ocean. All right. No fool on this, crew. That is absolutely true. Let's see what that does to our next lineup. We have some shifting, but the fast elk is still holding on tight. True and false. No creatures can live within the sea ice. True or false? No creatures, no living things can live within the sea ice. True or false? All right. False is absolutely correct. We know that there is life that forms the base of the food pyramid in the Arctic, which is why it's so important, that micro life forming the base of those food chains. And so that sea ice is really, really important for food chains in the Arctic, Antarctic as well. Ooh, the expert sea lion slips into first place. And we have one more question. When melt ponds warm, what do they do? Do they become cooler? Do they expand? Do they evaporate? Or they just don't change at all? So when melt ponds warm, do they become cooler? Do they expand? Do they evaporate? Or they don't change at all? We have 2 more seconds. Get those answers in. Ooh, a little bit of a split there, but we talked about how they expand. When that heats, the water heats, it melts more, the water expands, right? When things warm up, they expand as well. So let's take a look at our podium. In third place, we have the fast elk. Second place, the mighty bison. And holding down that top spot, ooh, the kind dolphin sneaking in right at the end.
Whoa, nice work.
All right. Well, very cool. Thank you so much, students. We love playing a little Kahoot. It's a nice way to interact a little bit. So thanks for joining us with that today. Let's switch gears now and go to some Q&A action. So we're going to start meeting some of our students and we'll start taking some questions. So we're going to have to start. Let me bring up my page. There we go. Okay, we have to go to Toronto. We've got some grade 6s hanging out with Madame Better. So let's get them in front and center. Hey, grade 6s, how are ya? There they are. Very cool. All right, let's get that mic unmuted and let's get a question or two.
It was really nice to hear from you.
Oh, thank you.
On dit merci.
Merci.
No questions here.
Okay, well, if you change your mind, send a question in the chat or give me a wave so I come back to your crew.
Thank you.
All right. Mrs. Paget's crew. Where is Miss Paget's crew joining us from? They are in Cherokee, Texas. Very cool. Let's bring them in front and center. Hey, Texas, how we doing?
Good.
All right. Does anybody have a question? It can be anything about sea ice or being on expeditions. What do we got?
Why is that your favorite instrument?
That's a great question. So I really like to go for walks and I really love seeing things all over the floe. The ice can look completely different depending on where you are. So using that instrument requires you to walk a lot, but you also get to collect a lot of measurements quite quickly. You just hit a button and a measurement's taken. So you can just walk along, hitting the button and taking loads and loads of measurements. It's really cool.
All right. Do we have another one there or do you want us to come back? Oh, we do.
How many animals did you see?
Oh, so many animals. It kind of depends on where you are in the Arctic and when you're there. When we were in Fram Strait in May and June, we saw so many polar bears. There was I think a visit every day from at least one polar bear. So it varies a lot, but that was a lot of visitations by polar bears.
All right, very cool. Well, if you have another question, we'll try and swing back your way. Okay, Texas?
Okay, thank you. Thank you.
All right.
Thank you.
So our next crew is another Toronto class, some more grade 6s.
There we are.
From
Ready?
There they are.
Hi.
Hi.
Okay, make it big.
Make it big. Huh?
Ask a question.
Wait, sorry. Where's the big?
Just ask the question.
Okay, just ask a question. Hi. My question is, where did you create the satellite, or did you borrow the satellite from somewhere?
Oh, so the satellite, this takes a lot of people to build usually, especially the big satellites. And it takes them about, 10 to 20 years to build a satellite and get it up into space and operational. What I do is I take the data from the satellite, so it sends it back to Earth. And then a center will send that data to all of these universities and data centers, and then I get the data that way. So the satellite's still going around, and it's sending us its data on a pretty much a daily basis, and we can just download the data and use it. It's a great question.
Okay, thank you.
Thank you.
Hi, my name is Abinadab, and how does the reflecting ice affect other planets?
Ooh, that's a good question. So I don't have a good answer for that. I'm not a planetary scientist. I don't think that the Earth's reflectivity affects other planets because they're so far away, but other planets' reflectivity control the climate of that particular planet. So the reflectivity of Mars or Venus will change what the temperature is like on those planets.
Okay. Okay. Hi, my name is Mahana. My name is Wahab. And my name's she is Savannah.
I'm Savannah.
Okay, so we had a question. The germ, the bug that's in the snow, what's the name of it? And does it have a habitat? And also, does it harm humans or animals, or does it harm the habitat of animals or the animal itself?
Okay, so those little like green things that was in the ice, so those are a type of phytoplankton. Their specific type is called a diatom. And they're really pretty. If you were to look under a microscope or if you Google diatom, they create these beautiful shells and it's like really pretty. It almost looks like artwork. But these are actually really important for the marine food web. So they're helping a lot of animals. Those little diatoms, once they get into the ocean water, they help feed zooplankton. So these are like little bugs in the water. And then other things eat those zooplankton like fish or birds. And also the stuff that fall from the zooplankton help feed clams, which then feed walrus and seals. So you can see it's kind of all interconnected. It all relates. The short answer is they help, they're good, and they're diatoms.
Thank you. Thank you.
You're welcome.
Right. Great questions. A classroom a little closer to some of your stomping grounds in Anchorage, Alaska. Miss Carton's sixth graders are hanging out with us today. How are we doing? All right, Anchorage, who's got a question for us?
Yeah, hold on for just a second.
Yeah.
Come on up. Me? Come on up. Yeah. And then Timmy, you could go too. Go ahead. I don't know why they can't see us, but that's okay. We're gonna go ahead and still ask our question. Go ahead.
Hi, my name is Bear, and I'd like to ask, how does the sea ice apparently reflect almost I have bad stuttering, 80% of the sea ice?
How does it do that?
How does it do that?
Yeah, it's super cool. So a lot of it has to do with the grain size of the ice, and especially the snow. So snow is a really good example. You've seen those really fluffy snowflakes that have like lots of things sticking out. These reflect a lot of light. You can think of something being really small has more opportunity to be reflected off of that surface. So if you have a lot of tiny little grains all together, there's a lot of surfaces that a single photon, light is made of photons. If that photon hits a surface, there's a good chance it'll be reflected back. But if it hits many of these surfaces, it'll probably get reflected back. Now that's an example of like snow and ice. Let's say I had a chunk of ice that only has like one surface. The light will probably get travel through the ice instead of getting reflected because it's not made of all these little grains. It's just one solid chunk. So that's kind of an example of why it can be so reflective. It's about how many little grains is it made up, and the grains each have little surfaces that can reflect that light. Does that explain, or does that explanation help? I can try again if it doesn't.
Yeah, that makes a bit of sense, even though my square brain can't handle that.
It sounds like it does handle it. Thank you.
Yeah.
And did you want us to wait for a second question, or
No,
do you
if
want?
you have your second, we can see you now. If you have your second
Yeah.
question, go ahead.
Yeah, go ahead, Timmy.
How expensive is polar science?
Ooh, it really depends. So if I'm going up to Reykjavik with a couple of people for a week, it's not too expensive. It can be maybe, $15,000. If I am doing a 6-month-long expedition on a ship, that can get really expensive. I think it would cost something like $100,000 per day to run a ship in the Arctic. So it gets a little expensive, but in those situations, you have many people coming together to share the money and to share the science.
Okay. Awesome, thank you.
I only have
Right.
$15 to my name.
Great. Great questions. Okay, we can squeeze in maybe a couple more. So if you want me to visit your class again, give me a big wave. And we'll try and squeeze in a couple more quick questions before you wrap up for today. I think I see someone running up to the camera in Toronto. So let's bring in George Webster's crew.
Okay, so I have a question. Hi, guys. Hi. My name's Abraham. So my question is that are the tiny bugs are poisonous?
No, they're not poisonous. I'm sure that scientists have accidentally eaten many, and it's okay. We're still alive.
All right. Is that somebody else coming in behind? All right.
What inspired you to do this?
Oh, that's a really good question. I had a really cool opportunity to go to Southeast Alaska and help scientists with their work. They were taking a lot of measurements near glaciers in this place called Glacier Bay National Park. And I was just amazed by how beautiful ice could be. And I was amazed that people could go ask questions and get paid to ask questions and answer those questions. I thought, okay, I think I'll go back to school. I'll get my degrees to go to these beautiful remote locations to see this beautiful landscape and just be curious and try to figure out how these things work. And it's been really fun.
All right. Another couple great questions. I see our crew in Texas waving like crazy. I'll be right there. But Madame Better's grade 6s in Toronto. I'm going to swing back to them from the beginning. They have a question for us.
How did you get food and water on the trip?
Yeah, it depends on which trip. So on the icebreaker, the one that was the long expedition, there would be ships and airplanes that would rotate scientists, crew, and food. So I showed a picture of those two ships together. Well, one of them came by the Polar Stern, the one I was on, and offloaded a bunch of food that way. If it's like we're working in Utqiagvik, there is a grocery store, but we also try to bring a lot of our food as well. You know, I like bringing my favorite snacks.
You just have one quick more.
Sure.
Did you guys have like bunkies or like where did you sleep?
Yeah, that also depends on the expeditions. So on a ship, you often have to share a cabin that has different bunks. Usually it's like 2 per cabin or 3 per cabin, or sometimes you can have your own cabin if you're lucky. When I'm working in Utqiagvik, it depends on the housing. So I often have my own room and don't need to share with others. But if it's a really big expedition and there's limited bunk space, you do have to share cabins.
All right. Great questions. We've got to visit Texas one more time and we'll wrap up with our crew in Alaska. I see them waving.
Go ahead. Did y'all drill ice samples?
We did. I want to say we took almost 200 ice cores. A lot.
What do you learn from them?
What do you learn from those?
Oh, we learned so many cool things. So, for instance, what type of biology is living in the ice? That's what some of the cores are used for. Other cores are used to understand why the ice is so reflective. So similar to a question before, like what does the grain structure look like and why is that causing it to be more or less reflective? Other people use it to test like the strength of the ice. How much do you have to squish the ice for it to break apart? So there's all sorts of different questions that people are asking, but use those ice cores for.
All right. Great questions. And one more trip to Anchorage.
Okay. My name's Kiana, and my question is, what's the weirdest or the most unique living thing you've seen?
Oh, yeah. I love that question because I did not expect to see something while I was on the Mosaic expedition. I found a starfish in the ice, and starfish do not live in sea ice. But what happened was this sea ice flow that we were on came from land fast ice. So this is sea ice that gets attached to land. And the starfish got stuck in the ice there and drifted across the Arctic. And then we set camp on it. And when the snow melted, there were starfish.
Really? Oh my God.
Yeah.
Very cool.
My name is Zabby, and I was wondering, do you know what piece of ice is the oldest?
Oh, we try to. So we use a combination of putting buoys on the ice to track where they go and how old they are. And we also use remote sensing to track ice. And, you know, we can identify ice that's older than 10 years old. But with climate change, this older ice is melting away. The Arctic sea ice cover is actually becoming younger over time because that older ice melts away each summer. So right now, there's not a whole lot of old ice. I would say the average age of the old ice is closer to 3 to 4 years old.
All right.
Yeah.
I have one more question. Have you ever fell beneath the ice?
Especially in the melt
Yes.
pot.
Yeah, I did once and I was totally safe. The only thing that was hurt was my ego. So I was wearing a dry suit. I didn't get wet. It's hard to tell thin ice when there's snow on top. The snow's so reflective, you can't really tell how thick the ice is underneath. I stepped on thin ice and broke through, but I was fine. I was just embarrassed.
All right. Well, I want to start off with a big shout out to our classrooms today on YouTube and our camera classrooms. Thank you for all those absolutely incredible questions. A few classrooms have had to duck out for recess, but we still have some hanging out with us. If you want to give a big wave and thank you before we say goodbye today. Thank you. And Melinda, thank you so much for letting us steal some of your time and taking us into the world of sea ice and how you're able to research it and what we can learn.
Oh, this is so much fun. Thank you. Happy to chat anytime again.
Excellent. Thank you so much, Melinda. Thank you, classrooms. We'll sign off for today, but we hope to see maybe some of your classrooms in World Rhino Day events tomorrow. Thanks, everyone.